Hey guys, today we'll be going through question 2 of the 2017 Maths Methods Exam 2 from the extended response section. The reason why I've picked this question is because this question is fairly difficult, especially towards the end. The later parts of this question became quite tricky, and a lot of students weren't able to get the full marks for it. So, yeah, definitely a very good question, and definitely a lot of good ideas for us to unpack here. And hopefully, some of the concepts that we learned today will help us in our later exams. Okay, so let's go ahead and get started. Um, just for a bit of context, we have a Ferris wheel, and this guy called Sammy is, in one of these capsules, and he's traveling anti-clockwise around the Ferris wheel, right? So he's traveling this way. So what's happening is, his the height of his car. So he's in one of the cars, so he starts at the bottom here, and he goes around all the way, and he stops when he does one rotation, right? Because he does one complete rotation. So he'll start at the bottom, go around, and stop when he gets out. Okay, so this equation here sort of models the height of his car above the ground, right? So that's what we have here. And this is the graph I've drawn, which represents one period of his motion, right? So this is something you could have just sketched in your CAS, right? You could have just sketched this equation in your CAS, sketched it for one period, and you would have got the same thing. So yeah, that's about it. That's about most of the context we need for now. And with that, we can sort of start part A. So part A wants us to find the minimum and the maximum heights of P above the ground. Well, that's pretty easy to do. We can obviously use the equation for that as well. Well, it'll be 65 plus 55 and 65 minus 55, as we know with these trig equations. But otherwise, we know we can look at the graph and we can see that our maximum occurs at 120 and our minimum occurs at 10. So max will be at 120 and min will be at 10. And don't forget the units as well. Okay, so how much time is Sammy in the capsule itself? Well, we are told that he only completes one rotation, right? Which is why I've only sketched it for one period. And you can see that one period only lasts 30 minutes, right? Because obviously T is modeled. T is time in minutes, right? And H is height in meters. Okay, so since we're only doing one period, we know that the one period is only 30 minutes. But another way we can do that is obviously do 2 pi divided by n, where n is the coefficient of the variable inside the the trig function, right? So 2 pi divided by pi on 15, which is the same as 2 pi times 15 on pi. Pi's cancel out, and I get 30 minutes. Okay, cool. That's part A and part B. Part C, a little bit more difficult. You want to find the rate of change with h with respect to t, right? So obviously we can't do this by hand, but given that we've already defined in our CAS, h dash of t, we can quite easily do it if we've defined in our CAS. So the first derivative, h dash of t, is given by 11 pi on 3 times sine of pi t on 15. Here we want to state the value of t at which the rate of change of h is at the maximum, right? So you want to find not when h is at its maximum, but we want to find where the rate of change of h is at its maximum. So that's a bit different, right? So in order to find when the rate of change is at its maximum, we need to find the second derivative. We'll probably need to use the second derivative, right? We can't just use the first derivative because the first derivative will only tell us when the value of h will be at its maximum, not the value of the rate of change of h. But turns out we don't actually need to know, and we don't actually need to find the second derivative. All we have to do is just examine this equation here. So this equation here gives us the rate of change of h. So okay, so that gives us the rate of change of h. Yeah. Um, Obviously we know that our sine. So if I just draw a basic sine graph of sine of x, right? In our basic sine graph, um, we reach our minimums, our peaks and troughs at pi on 2 and 3 pi on 2. Yeah. Okay. So when we reach pi on 2, that's when we have our maximum, right? Essentially, when this inside term here is pi on 2, sine will reach its maximum. So we don't actually need to, find the second derivative and then solve for it to equal 0. All we really have to do is just solve for pi t on 15 to equal pi on 2. Because I know that when this equals pi on 2, at least for the first period, because obviously there can be more periods and stuff, But because we're only looking at one rotation, right? So we only have to worry about the first period, right? That's why we solve pi t on 15 is equal to pi on 2. Pi's cancel out, so I end up with 2t is equal to 15. T is equal to 15 on 2, which is equal to 7.5 minutes. Yeah, so that's the value of t at which rate of change of h at its maximum. Okay, let's move on to part D now. So part D, not too difficult either, but just requires a bit of thinking. And I mean, part D and part E will require a bit more thinking, but it'll be a bit more involved. Okay. Anyways, we should recall that the equation we actually have for h of t is given by 65 minus 55 cos pi t on 15, right? So its median height, the middle height, will be at 65. That tells us that this point here, C, is given by 0.65. And we can actually verify this later on with when we start doing part E. But yeah, this point C has coordinates 0.65. And given that, we can actually just use the tan inverse function in order to solve this problem. Because we know that the distance of this point B, so point B is described as a stationary boat where, when we get to this point P1, that's when it's first visible, right? So we can actually just find this angle here by considering the height. Height of this is 65, obviously. So we have the opposite side and we have the adjacent side. So we can use our tan inverse function in order to find theta, right? So theta will be tan inverse of the opposite over the adjacent side, so 500. And you'll end up with something that looks like 7.406912128, blah, blah, blah. All you have to do is find it correct two decimal places, so I just have to round this to two decimal places. Hence, theta is equal to 7.41 degrees. Okay, cool. We're told that part of the path of P is given by this equation here, where x is between negative 55 and 55, right? So what do we have here, right? What we actually have here is part of the equation of this circle, right? So it's telling us that it's part of the path of P, but how do we know which one it is? Well, I can quickly show you actually. Well, this circle has a radius of 55, as we know, right? So we have a radius of 55. Therefore, and we also know that the center point has been shifted upwards, like from a basic circle, its center point has been shifted upwards by 65 units. Therefore, it looks something like x squared plus y minus 65 squared is equal to the radius squared, so it's 55 squared. Then if I just isolate y, right, and I'm going to get y minus 65 squared is equal to 55 squared minus x squared. 55 squared is indeed 3025, so that we'll write that down, plus or minus square root 3025 minus x squared, and then I'll add the 65 to both sides. So y will be 65 plus or minus the square root of 3025 minus x squared. Okay, so what does that mean? Well, what we actually should know is when we have a circle, our circle is a relation, right? Because it's not really a function because it doesn't pass the straight line, the vertical line, and nor does it pass the horizontal line test. Okay. When I express it explicitly in terms of y, the reason why I get 65 plus something and 65 minus something is because I'm trying to express it in terms of two separate functions. So when we talk about 65 plus that, we're actually just talking about the top half of this circle. And conversely, 65 minus that will be talking about the bottom half of the circle. Okay? So when it tells us this, that tells us that we're only considering the top half of this circle. Okay? Now, so this equation here, that pretty much just describes the top half of this circle, of the path of P, of Sammy's car. Anyways, we can define this in our CAS. We can also do it by hand, but we might as well define it in our CAS and try and solve it because it'll be helpful later on. So finding dy dx, just put it in the CAS and you'll get negative x on the square root of 3025 minus x squared. Okay, and that's about it for now. We'll move on to some of the trickier parts. So as you can see, part F, part G, and part H, they were the most tricky parts in this in not only this question but the whole exam itself. So there are quite a few ideas for us to unpack here and for us to sort of consider properly. So part F first, right? We want to find the gradient of the line segment P2B in terms of u, and then we want to find the coordinates of this point P2. Okay, so how do we sort of find the gradient? So how do we find the gradient? Well, hopefully you remember from part E that we were asked to find dy dx, right? We were told that so we were given the path of the top half of the circle, like we were given an equation that described the top half of the circle, and we are told that this point P2, right? We're told that this point P2 is tangent to this path of P, right? So this point P2 is tangent. So if I go from B to P2, this line through P2 and B, that's going to be tangent to this circle, right? So if I know that dy on dx, so if I just write it up here, dy on dx was, from the previous question, was negative x on the square root of 3025 minus x squared. So if I know that dy on dx is equal to this, right? If I sub in u, dy dx given, x is equal to u, then dy dx is going to be negative u on the square root of 3025 minus u squared. So why is that relevant? It's relevant because when x equals u, that is exactly the gradient of this line. Yeah, when x equals u, because the gradient when x equals u is the gradient of a tangent line at this point P2. And since this line from P2 to B is indeed tangent to the path of the circle, then I know that this must indeed be the gradient of that line segment P2B, right? So yeah, that's what we have so far. Okay, so we found the gradient of the line segment P2B in terms of u. So we've got that first part done. But we want to find the coordinates of P2. So how do we do that? In order to do that, right, we sort of need to find what u is. We need to find out what u is. And since we only have one part of it in terms of u, so we only have dy dx in terms of u for the gradient of this line, we don't really have much chance of finding out what u is because there's nothing for us to compare it to. See, there's no like equal sign for us to sort of solve an equation. So we have to find another piece of information that will, represent the gradient of this line. Turns out that's actually not too hard to do because, we've sort of been given the coordinates of this point B. We're told that it's 500 meters away from O, so its coordinates are 500, 0. We're also sort of, if we draw a straight line from this point P2 all the way down here, we also know that, so obviously we know that if u is the x coordinate, then this bit here is given by u, and that bit there, from, that point there to that, to all the way to B, that's given by 500 minus u. Okay, so next thing for us to do to find the gradient is just basically for us to use y2 minus y1 over x2 minus x1. Just how we would basically find the gradient from from basics, right? Whenever we have a line and we're given 2 points, we can find the gradient of the line from taking the first y coordinate minus the second y coordinate over the first x coordinate minus the second x coordinate. In this case, we want to express the y coordinate because the y coordinate is given by v. We want to express the y coordinate in terms of u as well, in order for us to eventually then find out what u is, right? So we know that the path, we know that this line, or I guess the equation of this path is given by y is equal to square root of 3025 minus x squared plus 65. Therefore, if I sub in u, that means v must be square root of 3025 minus u squared plus 65. Okay, so if I call this point P2, so if I call v y2 and if I call 0 y1, then I'm going to get 3025 minus u squared plus 65 minus 0. So that's y2 minus y1 over x2. x2 is going to be just u minus x1, which is 500. Okay, So now all I have to do really is just equate these two sides in order for me to find u. So if I make them both equal each other, so if I make them both equal each other and I solve for u, I end up getting u is equal to 12.999748. So yeah, so that's what my x coordinate of P2 is, right? And then to find out the y coordinate, all I really have to do is just sub in this point u here. So I want to find v, right? So I can sub it in to, this equation here pretty much for u. And given that we've already defined in our CAS, as I mentioned before, it would have been helpful. So hopefully, we've defined in our CAS. So once I sub it in there, v will now be 118.442. So yeah, not too bad actually. It's a bit tricky, but as you can see, it was pretty. I mean, it wasn't. It didn't take. It wasn't. It wasn't that difficult to find out what these coordinates were. All we really had to do was find the gradient first in terms of u, right? Because obviously we need to realize that this line P from P2 to B did represent the gradient of the circle at this point at that point u. We needed to know that there was a relationship between the equation we got from part E and this and what we're doing now in part F, right? And once we got that, all we had to do was use the basic gradient formula, y2 minus y1 and x2 minus x1, in order for us to find our coordinates. Yeah, so hopefully that was okay. Hopefully you guys managed to understand everything from that. But do let me know if you have any questions. So anyways, you have this. So we wanted two decimal places. Our x coordinate is going to be 13, because obviously if I'm rounding up 999 to two decimal places, I'm going to go to 13.00. So yeah. And then our y coordinate is going to be 118.44. Okay. Yeah. And yeah, just remember that when I round up, in this case, I need to write the two zeros because there are still numbers coming after it. So um, I can't just write 13, even if it is 0 afterwards. Okay, cool. Now we go on to part G. So we want to find this angle alpha in degrees to two decimal places. So it looks a bit difficult. This one looks a bit difficult as well, but it actually isn't really. All we have to do, so we know what the point, so all we have to do is pretty much the same thing, right? This height here, we know the height here is V, and this length here, we know it's 500 minus u, and that makes a triangle, which gives us alpha, right? So again, we can just use our tan inverse formula. So tan inverse of v on 500 minus u will be, whatever alpha is, right? And, we can very easily just do that. We know what v is. We can take the answer from, obviously copy and paste it. So because you want to avoid any rounding errors, so copy and paste it from your CAS into the next part of the question. So put v up there and then put 500 minus u, put it over 500 minus u, and then, take the tan inverse of it, and you should end up with 13.67 degrees to two decimal places. Okay, so now finally we have part H. So part H was definitely the hardest question in this exam. It was a very difficult question, so hopefully we can sort of unpack this together and see how we can go ahead and do this. Okay, so we're asked to find the length of time during which the boat is visible. Okay, hopefully so obviously we remember, right, what our equation is. Our equation that was originally given to us at the start of the question, h of t is equal to 65 minus 55 cos pi t on 15, right? So you want to find, I guess, the interval of time such that the boat was visible during the interval of time. So if you remember, the boat was visible from P1, so from this point P1 here, and then up till the point P2, it was visible during those times. Yeah. So P1, let's just call the coordinates of P1. Let's just give it a random set of coordinates. Let's say it's S and N, right? And obviously P2 is U and V, right? So what do we see here? Here we have an equation um, in terms of time that outputs the height at that time, right? We know that at a certain time, the height of our so at a certain time, the height at P2 was 118, but we don't know what the height was at this point P1, right? Because obviously we can find the time when the height was 118 by just solving for that, right? And we can do that now, right? So when at P2, right, we take this value here, 118.442, we solve that with this equation here, 65 minus 55 cos pi t on 15, right? So we solve this equation here. Just make sure that when we do end up solving this, you put in a bound, right? Because you don't want to get just make sure when you do end up solving it, you put in a bound because you don't want to get values that are above like 30, right? Because you're only doing one rotation. We're not doing any more than that. So we're going from t is between 0 and 30, and when we solve this, we'll get t is equal to 13.8608. So yeah, so something like that, right? Um, cool. We actually do get two answers, but the reason why we take the first answer, 13.8608, is because of the fact that so essentially what's happening is we have a circle here. We start at the bottom and we go around, right? And after we go around, it's been 30 minutes, right? So the reason why we take 13.8608 and because we did get two answers, we got 13.8608 and we got 16.1391. The reason why we choose the first answer and not 16 is because point P2 is obviously before the top of the circle, right? After we pass the top of the circle, the board is no longer visible, so point P2 is somewhere there, right? It only makes sense if we are going around the circle one time and it takes us 30 minutes to go around the circle for us to be at this point after 15 minutes, which means it's only logical for us to have got to this point P2 here at t equals 30 minutes, which is why we only take the first answer. But anyways, yeah, that's the time when we got to P2. Um, Now we need to find the time when we got to P1, right? But it's a bit harder for us to find the time when we got to P1 because we don't know what the height was at P1. So there's nothing for us to solve. So in order to do this, we need to be a bit clever with it. We need to use some sort of geometry. So there are a couple ways to do it, but I believe the most intuitive way is to just use a bit of geometry in order to solve for the height of P1. So what I'm going to do is I'm just going to create like a small triangle here, right? From the center of the circle up there to this point down here. That's at the same level as P1. And yeah, so I've just joined these 3 points together to create a small sort of triangle. Okay, so if I'm just going to reproduce the diagram on the side here, what we have is something that looks a bit like this, right? So we have the circle, this is the ground somewhere here. We have the center of the circle. We have the point P1 here, and this point on the y-axis that's on the same level as P1. I'm sort of making a triangle with these three points. Okay, and that's the point P1 here. So our goal is to find this distance. I mean this length here, right, which is the height of P1. That's our goal. What do we know? So we know that this angle here, or at least this angle here, right, is the same as that angle here, because these two triangles, because I've made this triangle, smaller triangle here, I made it inside the bigger triangle, right? So we know that these two are similar triangles, therefore we know that these two angles are the same, right? So if these two angles are the same, then we know that this angle here is equal to that value there. So theta, or whatever you want to call it, theta is equal to 7.4069121, blah blah blah. Okay. We know that the height of C, we know that that is 65, right? So this we'll call x because that's what we want to, we don't know, right? That's what we don't know, right? That's what we want to know. So that's what we'll call x. Um, and we do know the length of the hypotenuse actually of this triangle. We know the length from C to P1 because that's just the radius of the circle. The length of C to P1, that's just 55. Therefore, um, for us to find the value of x, what we can do is we can just use the sine ratio. So sine of theta, given that we're using this value of theta, which is 7.4069121, right, is equal to the opposite side. So if this length here is 65 and the whole height of C is, if this length here is x from this point down here all the way to this point down here, and that point down there to that, and up there to this, the origin is 65, then this length here must be 65 minus x, right? So opposite side has length 65 minus x, and our hypotenuse has length 55. Okay, so all I have to do again is just sort of put this into my CAS, right? I put it into my CAS and I'll solve for sine of 7.4069121 blah 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 is equal to 65 minus x on 55. Okay, just beware though that if you're working with radians, so if you're working with radians, obviously you can't put in, it's wrong for you to put in 7.46921 radians because this is a value in degrees. So you need to multiply that by pi, right? So multiply that by pi and 180. So convert it to radians and then solve the equation. But yeah, once you do that, you should get the x value, which is the height of the point P1, which is what we actually want. The height of the point P1 is equal to, so the height of the point P1 is equal to 57.90966233, blah, blah, blah. Okay, so given that we know that, now we can find when we were at P1. So at the time when we were at P1. So take the same value there, 57.90966233 blah 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 is equal to 65 minus 55 cos pi t on 15. And again, make sure you put the same bounds in. T is between 0 and 30. And again, you're going to get two answers actually. You'll get t is equal to 6.8827, which is actually what you want, right? And you also get t is equal to 23.11724. You don't actually want that because obviously, as I mentioned before, we have this, imagine we are traveling around a circle. If you start here, and it takes us 30 minutes to travel around the circle, we start here and we end up here, it's only going to take us 15 minutes, right? So anything beyond 15 minutes is when we are traveling around this part here, and we're not concerned with that. Okay, since P1 is somewhere down here. So we'll take this value, 6.882757. Then, because that's when we are at P1, that's when we are at P2, and between those times is when the boat was visible. Therefore, to find the total time during which the boat is visible, if I can just call this T2 and T1, so subtracting that, T2 minus T1, I'm going to get, or when I round it off, I'm going to get 7 minutes. Yeah, so there are a few different ways to do this question. Maybe some ways might be a bit more intuitive to you, but I believe this way is the most intuitive way. Just using a bit of geometry to find the height of P1, and then once we do that, we can just use the equation we've already been given at the start in order for us to find the two values of t, and then we subtract the two values of t, the first value of t from the other, in order to find the total time that we were traveling around the circle for, or around the Ferris wheel for in this case. So yeah, hopefully all that was clear. If you do have any questions, feel free to text me or I'll mention ask me in class. But yeah, hopefully that was all clear. I will see you in class. Bye bye.